Okay, welcome to the lecture on density functional theory. So I'm going to try to give you a brief introduction to what DFT is, basically, and a little bit about how it works. If anybody has this book, Computational Chemistry, Frank Jensen. I think it does a nice job of giving you a kind of a brief introduction to the topic. So I'm going to kind of go over some of the things that are in there. So big picture, what is DFT? DFT is a way to solve the electronic Schrodinger equation. So it's an alternative to, for example, Hartree-Fock theorem or configuration interaction. In fact, by the time you write down the equations, it looks really similar to Hartree-Fock theory because you borrow some of the technology from Hartree-Fock to make one of the terms easier to deal with. The cost is cheaper than Hartree-Fock if you use some tricks and you use some approximations for how to deal with exchange. This was this K matrix that we had in Hartree-Fock theory, or two electron integrals that looked like IJ. That would be an exchange integral. Those happen in Hartree-Fock. They also happen in density functional theory. DFT tends to have approximate ways to handle exchange, and those would be exchange functionals. We'll talk about what a functional is in a second. If you use those and use sort of typical exchange functionals, the computational cost of DFT formally scales as n cubed rather than n to the fourth like Hartree-Fock. Now both of them you can reduce down to n squared or even order n linear scaling if you do other tricks, but ignoring other tricks, DFT formally looks like n cubed if you're using an approximate exchange functional. However, it turns out that DFT tends to be more accurate when you don't do that and you use actual Hartree-Fock looking exchange. And when you do that, the cost goes back to n to the fourth, so it looks the same as Hartree-Fock theory. Again, n to the fourth before you start doing other tricks that might reduce it. So the computational cost is similar to Hartree-Fock, especially if you use Hartree-Fock exchange. Those are so-called hybrid functionals. And the accuracy, however, is almost always better than Hartree-Fock. You get a pretty good answer out of DFT. So at the price of doing something that looks a lot like Hartree-Fock plus a little extra bits, you get something that's more accurate than Hartree-Fock and is good enough for a lot of chemistry. You get very reasonable chemical structures, bond lengths, vibrational frequencies. Actually, you have to work really hard to beat the vibrational frequencies you get out of DFT. They're really quite good. So things like that are great. Other things like excited state properties that you would get out of time-dependent density functional theory are not as accurate. It just kind of depends on, is it a valence type excitation, then it might be pretty good. If it's a so-called Rydberg excitation, where you excite out to a big orbital somewhere, then it might not be good unless you make some corrections, like so-called asymptotic corrections. What else? DFT for reaction energies. If you're getting like an enthalpy of reaction, it's probably pretty good. Definitely better than Hartree-Fock. But not necessarily as good as, for example, couple cluster theory. However, couple cluster theory, since it scales as n to the seventh formally, is way more expensive than DFT. And so if DFT is good enough, then you'll probably just stop there and just use it. Reaction barrier heights, so activation energies, are often a little off with DFT. It depends on your study whether it's off by enough that you care. But barriers are typically off by a few kcal per mole. So, if you're just checking whether a barrier is like 30 or 50, it doesn't matter. But if you need a barrier plus or minus 1 kcal, DFT is probably not going to do it for you, and you're going to have to do coupled cluster theory. Since reaction rates depend very sensitively on barrier heights, if you're trying to do dynamics, this actually can be a pretty big deal. You need the barriers as accurately as you can get them, and the DFT may not cut it. So that's a little bit about what it is and how it works. If you were, I've already mentioned it sort of looks a little bit like Hartree-Fock theory plus some extra bits. If you have a Hartree-Fock code, you can adapt it by adding some extra pieces to do density functional theory. So most of the quantum chemistry programs that are out there, like QChem or Psi, they have a DFT module and a Hartree-Fock module that are the same module, and then there's just extra subroutines that get called if it's DFT. All right, that's it by way of sort of a brief introduction of what it is. Now let me tell you a bit more background and how it actually works. Close this. Okay. Oh, I should mention, I was mentioning things it has trouble for. I forgot to say, if you have charge transfer states, the Breda group is especially interested in charge transfer states. So charge hops from one part of the molecule to another. DFT has trouble with that unless you go in and do something to fix it up. Okay, so what is density functional theory? Well, the main concept is that it works with rho of R, which is the density, not the wave function. Now the wave function, it's a function of what? All the coordinates of all the electrons. And the nuclei, if we're doing a whole wave function, but normally in electronic structure we're talking about the nuclei fixed and we're solving for the electrons. But the electrons, remember I've been calling them coordinates x1, x2, whatever, and by that I don't mean coordinate x, I really mean x vector, which denotes x, y, and z coordinates plus a spin coordinate, which I've been calling omega. So there's 4 coordinates for every electron, and there's however many electrons there are, call it capital N. So this guy is a function of 4 times n coordinates, which if you had a little segment of DNA or something like that, that's a lot of electrons. So it's a highly multi-dimensional function. And it becomes, at some level, just a real pain to deal with. The density, on the other hand, is pretty awesome because it's a function of 3 coordinates, x, y, and z coordinates in space. What's the density? Or maybe you'll get a density for the alpha electrons and then a density for the beta electrons. But then, so what? Then you have 2 functions that depend on 3 coordinates. So just in terms of mathematical simplicity, the density is a much easier quantity to work with. But the problem is we know how to formulate quantum mechanics in terms of the wave function, not of the density. So the fact that the density is a simple function at this stage seems sort of irrelevant because, you know, how do you compute the energy of a density or how do you compute properties of a density? That was the great advance made that founded density functional theory by Hohenberg and Kohn, where they realized that you could actually work directly with the density. And a density functional, a functional is just a function of a function. The density is a function. A density functional is a function that you input the density function into and you get something out of. And the one we're most interested in is an energy density functional. So you put in the density, you get out the energy based on that density. That's a density function. Now, Hohenberg and Kohn showed that this function does exist. So there is, in principle, a unique functional that if you give it a density, you'll get back an energy. And from that, if you have some means of computing the density directly, you can get its energy out, which is great. The problem is we don't actually know what this functional is. So it's kind of an existence theorem, not a derivation of it or anything. And in fact, it's commonly thought now that even if we had the exact density functional, it wouldn't actually be all that useful because it's likely to be very, very complicated and computationally expensive. But that's okay. Just the idea that you could work directly with the density and get an energy out inspired folks to say, well, I don't know what the exact density functional is, but let me cook something up that might be reasonable. So we now have lots and lots of approximate density functionals where we're not getting the exact energy back out when you feed it to density, but we're getting a reasonable energy back out. And that's what we use in actual density functional theory. We have a bunch of approximations to this that we use. And there are quite a few of them out there. These approximate density functionals are basically tested by experience. So you make one up, you try how it works. Maybe sometimes you check whether it satisfies certain mathematical bounds that the exact functional should satisfy. You would think that making a functional satisfy more and more of the bounds that it should satisfy would make it a better functional. Sometimes it does, maybe not always, but there's a lot of thought and research that's gone on to getting these better functionals. Unfortunately, there's not any existing hierarchy of functionals that are necessarily better and better as you add more computational expense or more terms for a particular problem. There is kind of a hierarchy in terms of there are functionals that have more components to them than others, and in principle you would hope would be more accurate, and oftentimes they are, but not necessarily. So for a given problem, if you use functional X and you find out that your comparison to experiment is pretty bad, and you say, well, I'm going to have to work harder, let me use the next more complicated functional, you're a little bit stuck because there isn't the next more complicated functional. So this differs a little bit from standard wave function theory like perturbation theory or couple cluster theory that you'll hear a little bit about later. In perturbation theory, you could always go to higher orders of perturbation. In couple cluster theory, you could go to higher orders in the couple cluster series. Now, it's also true there that you're not guaranteed to get a better answer for any particular problem. But especially with perturbation theory, sometimes the perturbation series doesn't converge. But with something like couple cluster theory, if you add more terms to the couple cluster theory, you almost always will get a better answer, especially if you're careful to choose appropriate basis sets as you go up. So CCSD parentheses T is almost always more accurate than CCSD. CCSD TQ, if you could afford that, would be almost always more accurate than CCSD parentheses T. So we really do have a hierarchy in wave function approaches that isn't quite there in DFT, unfortunately. All right, so let me tell you a little bit more about these functionals. They're divided up into three parts, analogous to the three terms in the Hamiltonian. So my electronic Hamiltonian consists of electronic kinetic energy, that goes into the one electron terms, we talked about that already. Electron nuclear attraction, that also gets folded into one electron terms. And electron-electron repulsion. And this one we've discussed as being kind of the tricky one. So the energy functional, the density functional, takes the density, and it's normally written kind of as these three parts. There's a kinetic energy density functional, an electron nuclear attraction functional, and an electron-electron repulsion functional. All right. Now, do we know anything about what these are? Well, one of them, at least, seems pretty easy. This electron nuclear attraction one. That one we really ought to be able to write down because it seems fairly easy. So let's write it down, see what it looks like. Okay, electron nuclear. Well, I need this, oops, let's do that outside. You need to sum over all the nuclei. And then for each nucleus has got a charge Za. It interacts with the electron density. Now here, it's a density, right, not a wave function. So I don't write any size, but I do have the density. I'm going to write that rho of r. Let's assume for now that's just a total density of all the electrons, alpha and beta. And the distance between the particular point that I'm probing the electron density and the nuclear center is a capital Ra minus r, absolute value. So what is this? This is Coulomb's law, saying that for some spread out electron density, it interacts, it's attracted to a nucleus, Za, by this amount. It's the product of the charges divided by the distance, and 4 pi epsilon naught is 1 in atomic unit. So this distance. And because the electron density is all smeared out over space, I can't probe this at discrete points. I need to integrate over all possible points. So that's what I'm doing. And so you integrate over all space. At each spatial point, I know how much electron density is there, and it's attracted to that nucleus by this amount. And so the integral of this and summed over all nuclei gives me the electron nuclear term. And I didn't write a negative in my notes, but somewhere there needs to be a negative sign because it's an attractive term. Maybe I'll add that out here or something, because we know electrons are attracted to the nuclei. So if you did have a smeared out charge density of electrons, that would be the attraction to the nuclei. So that actually is not that hard. You just have to be able to do this integral, which is not as tricky as some of the ones that we've encountered. Only depends on 3 coordinates in this case. How about these other 2 bits? The kinetic energy density and the electron-electron repulsion. Let's talk about the electron-electron repulsion one first. All right, well, at some level, we would expect it to look something like this, right? You have electron 1 has some density, electron 2 has some density, and they repel each other by Coulomb's law. So you would expect the numerator to look like a density times a density divided by the distance between the electrons, integrate over all the possible locations of electron 1 and electron 2. That's going to be a 6-dimensional integral instead of 3-dimensional, but that's okay. I'm going to call this J of rho, and I'm going to divide by half to avoid double counting. Rho of r times rho of r prime divided by the distance between r and r prime, integrate with respect to dr and dr prime. That's the classical Coulomb repulsion between 2 smeared out charge distributions. And because it's Coulomb repulsion, I called it J to be consistent with our Hartree-Fock notation. So in Hartree-Fock, we had these J integrals that look like IIJJ and things like that. Here I don't have orbitals yet, so I just have densities. All right, that's cool. And the 1/2 avoids double counting. But what I'm missing is what are the energy contributions coming from the fact that I want the electrons to say anti-symmetric. Remember, we have this anti-symmetry principle. That was built into our Slater determinant. Here I don't have any Slater determinants yet. I've just got density so far. So how do I enforce the anti-symmetry principle, and what's the energy correction to this due to the fact that the electrons need to be anti-symmetric? In Hartree-Fock theory, we wind up getting these K integrals. So what is it that I'm going to do here? All right, well, it's not super obvious what to do here, okay? So another gigantic advance in density functional theory was due to Hohenberg and Kohn, and they had some suggestions that wound up being super helpful, and nowadays much of density functional theory is using their ideas, and so we call it Kohn-Sham density functional theory. So what was it that Kohn and Sham suggested? And it's particularly this kinetic energy term that Kohn and Sham help us solve. That's the one that really holds us up. right, so let's talk about what Cone-Sham said we should do to deal with T. Oftentimes it's called KS, density functional theory, Cone-Sham. So they realized that if the electrons are non-interacting in the Hartree-Fock sense, remember in Hartree-Fock, each electron only sees an average charge field of all the other electrons, and explicit correlations between electrons are all kind of washed out. So you don't have what we call electron correlation in Hartree-Fock theory. They do see each other, but only in this average sort of way. And then once you do the averaging procedure in Hartree-Fock, each electron you solve, you have a separate Hartree-Fock equation for each Hartree-Fock orbital. You have a Fock operator times the orbital, gives the orbital energy times the Fock operator times the orbital back. And so each electron gets its own orbital in that kind of sense that they're sort of quasi-independent electrons, so they're sort of non-interacting. Then one could just use the Hartree-Fock expression for the kinetic energy. Using orbitals. Okay, so far in this discussion there haven't been orbitals. Now all of a sudden we're going to say, yeah, orbitals are kind of useful. Why? Because if I had orbitals, I would know what the kinetic energy was, because I can calculate the kinetic energy of an orbital. If the electrons are at some level independent of each other and occupying some orbitals. All right, so what is that? Now, assuming each electron is in an orbital, well, I'm going to call that T sub S. I'm going to sum over all the electrons, and each electron is going to be in an orbital phi I, and if it is, then the kinetic energy is just this. Integral of phi I star minus 1/2 del squared phi I, and this is going to take derivative of this guy with respect to your 3 Cartesian directions for that electron, x, y, and z. Second derivatives. All right, so if I throw orbitals back in kind of as a crutch, then I know how to compute the kinetic energy of that. And that's a perfectly fine expression. How do I connect the density back to the orbitals? That's easy. The density is just a sum over all the occupied orbitals. Phi I of R absolute value squared. And just as a reminder, absolute value squared just means phi I star phi I. Okay, so psi star psi is the chance that you see the electron at some particular place. So that's the density. Okay, now the problem is it's not really true that the electrons are totally non-interacting. Remember, Hartree-Fock's an approximation. So if I use the Hartree-Fock expression here, I'm making some kind of approximation. But to the extent that Hartree-Fock works pretty well, it's not an unreasonable approximation. Okay, and in fact, I could say something fancier about that, but for an introductory talk, we'll let it go at that. All right, so what does that mean? My density functional approximation in Cone-Sham approach, I'm going to have this kinetic energy of the electrons here. I'm going to have the electron nuclear attraction that we just talked about a minute ago, which was pretty easy to write down. I'm going to have Coulomb repulsion between the two densities, which is not hard to evaluate. And then I'm missing what? Well, I'm missing the fact that there somehow has to be some correction for the exchange energy from antisymmetry, which I still don't exactly have figured out. So that's going to be an exchange term. And then there's also sort of a correction for the fact that these are not truly non-interacting. We might call that a correlation term. I'm going to lump those together and call that the exchange correlation term, EXC. Now, what is EXC? Well, in a way, it's kind of a fudge factor. I mean, we kind of know what goes into it, but we don't know how to write down an exact equation for it. So you cook something up, or if you knew what this was, then formally I know what this is, because this is just this guy minus these three. But the problem is I don't actually know this unless I have some small system and I am very tricky, and maybe on a case-by-case basis I might be able to derive something like that, but not in general. So we pretty much just have to kind of do our best to figure out what to do with this guy. These other three are pretty straightforward. They're just what I wrote down earlier, and that's what people use. So the different flavors of density functional theory, unless you're doing something really kind of out there, are basically the same here, here, and here, and then they differ by doing different approximations to this exchange correlation energy. And in fact, you could split that term up into two pieces, one just for exchange and one for correlation, and that gives you so-called exchange functional and a correlation functional. And if you specify those two, you're specifying the kind of DFT that you're doing. There are people out there who do avoid Cone-Sham and don't use this formula, but use some other formula, but that's an active area of research. Chemists typically are not doing that right now. Physicists are playing around with this because it's a little more, for big systems, it's a little more expensive to work with orbitals. And if you could avoid orbitals, for big systems like 1 million atoms, you would. And so there are people trying to find other approximations that bypass the orbitals. But that's an area where people are really working hard right now. Okay, so just formally then, I think it should be pretty clear what this is already, but maybe this will clarify it for you even further. The exchange correlation functional then is correcting for the fact that the kinetic energy expression is not quite TS, so there's an error here that we're correcting for. Plus, it's correcting for the fact that the electron-electron interaction is not exactly J, because there's got to be some kind of exchange component. So that's the two sort of correction pieces we're adding, and the problem is we just don't know exactly what that is or what that is. Any questions about any of that so far? If not, where do I get these orbitals from? If you give me some orbitals, I can compute this without a whole lot of trouble. But where do I get the orbitals from? Well, it looks kind of like Hartree-Fock theory. So the Cone-Sham DFT equations look like the Hartree-Fock equations. There's a Cone-Sham one electron operator that acts on orbital I to give you orbital I back times some orbital energy. So in that sense, it looks like Hartree-Fock, except now instead of a Fock operator, I've got this Cone-Sham one electron operator. All right, what is this Cone-Sham one electron operator? Well, formally, it looks pretty simple. It looks like a Cone-Sham operator. It's got a kinetic energy piece, not surprisingly, plus the effective potential that electron I feels. All right, what is the effective potential electron I feels? Well, the effective potential at any particular point R is what? Its attraction to all the nuclei. That's in the VEN term. Okay? And then what else does it see? Well, it sees the other electrons. What is that? Well, there's a term where it's seeing just the average Coulomb repulsion of all the other electrons. So it sees some charge field rho, and Coulomb's law says the distance between them goes in the denominator, so that's the distance between them. Integrate over all other positions R prime. So that's basically just a Coulomb term that would go into J, plus whatever corrections there are to what I've just written down from the fact that, for example, it's not just all Coulomb terms, and from the fact that maybe I need some correction to this kinetic energy bit. So exchange correlation piece, which depends on R, and this is the mysterious piece that we have to somehow make up. The rest of it is all fun. All right, so yeah, it looks kind of like Mercury 5. This piece is the one piece that's going to be different. I'll just mention that there's something called an exchange correlation. Well, this exchange correlation potential here is the derivative of the exchange correlation energy with respect to the density. So if I had this functional, the density, its derivative with respect to rho would give me this potential. So I can connect that to that. Normally, as I mentioned a second ago, you actually break up the exchange correlation piece into two pieces. Maybe I'll put that here. Exchange correlation functional of rho. Normally I've split it up into an exchange functional plus a correlation functional. And typically I write that as an integral of rho of r times a little epsilon x of rho of r dr plus integral of rho of r epsilon of c rho of r dr. And these guys are like the exchange and correlation energies sort of per particle, and then we multiply those by the density to get out the total exchange and correlation energy. And likewise, there you could work out a potential version of these guys, which would be the derivative of these guys with respect to rho. But I think that's good enough for us now. Yeah, I think so. Okay, so what are some of the approximations that we make for these exchange and correlation potentials or functions? I'm not going to have time to go over them all, and for an intro lecture, it wouldn't be worthwhile to do that really anyway. But I want to say a couple words about some of the simpler kinds of them, and just give you a flavor for the different classes of approximations that there are. So let's talk about the easiest one first, which is the local density approximation, often called LDA. If you split out alpha density and beta density, you could talk about local spin density approximation. What is this? This is surprisingly easy. The exchange functional for LDA as a function of rho is just some constant Cx times the integral of rho to the 4/3 time of r dr. That's it. If you want this little guy here where you took the derivative with respect to rho, that's also easy. Sort of the per particle quantity is just minus Cx rho to the 1/3. So that you can do. That was not hard at all. Sadly, it's not super accurate. You can derive this from the so-called uniform electron gas. So you say, well, suppose electrons in a molecule were completely uniformly spread out. So the density is the same everywhere. Now they won't really look like that in the molecule. They'll be more dense towards the nuclei, et cetera, et cetera. But to start from something, and maybe further out in the molecule did you start to look like this. The density is just the same everywhere, and from that you can work out what this exchange has to be, and it's this. All right, so that one's easy to evaluate if you have your rho, which you would get from psi star psi for all the orbitals. You just plug it in this formula and get the exchange energy out. Easy. Actually, how would you do that? Normally, you make up some kind of grid that you evaluate this on. And there are various kinds of grids. You might have a Euler-Maclaurin radial grid and a Lebedev angular grid. And at different grid points, you would evaluate this and use numerical integration techniques. So, because this is a function of real space, not working in orbitals. So that's what you would do. I haven't said much about spin, and I won't today in the interest of brevity, but maybe for this one case, I will say a little bit about it. If the alpha and beta densities are different, when would that be? Well, if it's a closed shell molecule like methane or ethane, they'll be the same. But if you have an open shell molecule, like you rip an electron out of methane or something, and you have a radical, then alpha and beta densities will be different. So in a case like that, this is the so-called local spin density approximation. LSVA. And the exchange energy as a function of rho is minus 2 to the third Cx integral rho alpha to the 4/3 plus rho beta to the 4/3. So that's pretty easy. I just add the alpha and beta densities to get the total density, so it won't shock you. And then this little guy, for the per particle version of this, is minus 2 to the 1/3 Cx rho alpha to the 1/3 plus rho beta to the 1/3. Okay, so that's an easy one. Other cases, you do more tricky things than just adding the alpha and beta density. But for this one, you basically just add it. All right. This particular form of the exchange energy is due to Dirac, but it's often called Slater exchange. So this LDA or LSDA approximation to exchange, you could call it LDA exchange if you wanted, but a lot of times people just refer to it as Slater for short. And sometimes they don't even like to do that, they'll just put an S. So sometimes you'll see functionals like S-VWN. The S stands for Slater exchange or LDA exchange. And in fact, I mentioned VWN, so let me mention them some more. This was what happens if you assume a uniform electron gas and derive what the exchange energy is. What if you assume a uniform electron gas and derive what the correlation energy is? That's been done. So this uniform electron gas, if you derive the correlation energy, you can work that out. And this was done by Bosco, Wilk, and Musser. VWN, to give the VWN correlation function. And I think I'm not going to write down what that is, but it has a relatively, well, actually I think this one's done numerically. Anyway, this guy's tabulated. So frequently you'll see SVWN where this is the exchange functional, and then often you have a dash, and then you have a correlation functional after that. And together, this stuff would be considered basically a local density approximation. What does that mean, local density approximation? It means your formulas only worry about what's happening really where the density is and not somewhere else. That's good because if you're integrating and you only worry about where you're at, you only need limited information. You need to know what's the density where I'm at. Great, plug it in. Okay, I'm done. Unfortunately, this is also somewhat less accurate. You could kind of just like in a Taylor series, you could get a better approximation to a function if you say the function is equal to the function at some point plus the derivative of the function at that point times how far away you are from that point plus the second derivative at that point times how far you are from that point squared, et cetera, et cetera. Just like in a Taylor series, you could rewrite these kind of equations to deal not only with the local density, the density where you're at, but also the derivative of the density where you're at times how far you are from some reference point. So then you get a little bit more accuracy, and if you do that, those are the so-called generalized gradient approximations, or the generalized gradient approximation is where the functional depends not only on the density, but also the derivative of the density. So that tells you something about not only here's the value of the density, but here's which way it's changing. It's getting bigger, it's getting smaller in this direction. And that gives you a little bit more information to work with. So let me write that down because that's critical. Okay, so this generalized gradient approximation. This is usually called GGA. This is also called gradient corrected. A gradient corrected function, for example. Means that the functional, and here I'm really talking about the exchange correlation functional, depends on rho, and also on its derivative. Now, if I look at the derivative of the density at some point, that's still basically local information. I don't have to go off somewhere else and evaluate something. I'm still looking locally at some region of space, really. Unfortunately, in some of the literature, these things started being called non-local functionals. Because the idea is, well, if you knew the derivative, you could maybe guess what the density would be somewhere else if you didn't go too far. But that's the whole thing. You can't go very far. The derivative tells you the rate it's changing locally, but if you were to go very far at all, other things can happen. It's no guarantee that you'll have a good picture of what the density is elsewhere. So it's very bad that these were called non-local functionals because they're not non-local at all. It's just a really poor name. Sometimes people then went back in the literature and tried to sort of correct this and start calling them semi-local functionals. That's definitely a step in the right direction. But if you did truly need to know what's happening at some other point, you just need to go to that point to evaluate the density and the gradient there. You can't really extrapolate very far from a derivative or even a second derivative. All right, I'm not going to write them all down, but let me just list a few examples, to name a few examples of these GGAs. For exchange, there are PW91. As you might guess, these are often named after the inventors' names. This would be Purdue and Wang, and they came up with this in 1991. So that's why it's named that. Axel Becke came up with a very famous one in 1988, so it's called B88. Sometimes B88 is just called B because it's that famous that it doesn't need much qualifier. PW86. The most famous correlation functional that's gradient corrected is one due to Li, Yang, and Parr, which is called LYP. So just like here I listed the exchange functional first and then the correlation functional, I could do the same thing here, and so I could get GGAs like BLYP would be Becky GGA exchange plus Li, Yang, Parr gradient corrected correlation, or I could have all different combinations of these. Just to give you a little bit of a sense of what some of these look like, I'll write down one of them. Let's talk about the Becky exchange because it is very famous. The per particle Becky exchange B88 is, you actually start with the LDA exchange and then you add some correction terms. This is pretty frequent. A lot of times density functionals depend on other density functions. So you start with LDA exchange, you subtract beta times rho to the 1/3 times x squared over 1 plus 6 beta x inverse hyperbolic sine of x. What's x? X is a so-called reduced gradient. It's a gradient of rho divided by rho to the 4/3. So it's a little complicated. It's not infinitely complicated, and it's a kind of a correction to the LDA, which is sort of roughly correct, but it just needs to be kind of patched up a little bit. Okay, and then finally, let me introduce one or two last classes of these. So we went from local density approximation to generalized gradient approximation. Let's make one more step to so-called hybrid methods. And what these do is they start off with a Hamiltonian as a function of a perturbation strength lambda. It's the kinetic energy operator plus the so-called external potential as a function of lambda plus lambda times the electron-electron repulsion. All right, what in the world am I doing here? If you had lambda equals 1, this is the real system, and you get the correct Hamiltonian. And we'll call that the interacting limit. And in this case, the external potential is just the electron nuclear attraction, and I recovered the Hamiltonian I had a minute ago. What if lambda equals 0? This is the so-called non-interacting limit. Where T rho equals this Kohn-Sham approximation to the kinetic energy, Ts of rho. And in this limit, a single Slater determinant of the Kohn-Sham orbitals exactly solves the Schrodinger equation. Now, of course, a single Slater determinant made out of cone channel orbitals doesn't really solve the Schrodinger equation. But in this mathematical hypothetical limit that lambda were to go to 0, it would. All right, so who cares? Why do we care about this mathematical limit that would never exist? Well, once you set this Hamiltonian up to depend on this perturbation strength lambda, you can play a little trick with it. And in fact, one of the tricks we do is that if lambda is between 0 and 1, we adjust the external potential, which is the electron nuclear attraction in the limit of lambda equals 1. We adjust this thing such that the same density, rho of r, is obtained for either limit. So we're trying to find a smooth way to cross between the two limits that are interesting mathematically. And we just fiddle with this so that the density is always the same when it comes up. So this gives us a formal way to connect the interacting and the non-interacting limits. Then what you do is you write down the exchange correlation functional as an integral over this perturbation strength. Like this. This is the adiabatic connection formula. Basically gives you a formal way to get this exchange correlation energy. Now, can we actually just go ahead and solve this? Well, not directly. We don't really know how to do that. But now we make another approximation. If this exchange correlation energy, or potential, is linear in lambda, we can approximate this. And that's what we do. And then we get an interesting and useful result finally. We say, well, if it's linear, then the exchange correlation energy is about 1/2 the limit where you start at lambda equals 0, plus 1/2 the limit where you're in the real thing. All right, can I evaluate those two limits? If I can, then I have actually gotten somewhere finally. And the answer is, yeah, we can do something with these. All right, so what am I going to do? This guy, what is that? Lambda equals 0. That's the fake limit where the electrons are sort of not really interacting with each other. Well, psi 0 then is a Slater determinant. And we can use the Hartree-Fock equation for the exchange energy. Okay, so that's cool. What about this limit where the electrons are really interacting? Well, we don't know. We don't quite know how to handle that. We can do various things to approximate this. We could use LSDA, for example. But the idea is that I'm going to mix Hartree-Fock exchange, which is correct in this limit, with some stuff that I get out of density functional theory, like maybe LSDA. The simplest possible thing you could do is say, let's just mix half and half Hartree-Fock exchange with LSDA exchange or Slater exchange. So that would give me an exchange correlation functional, which I could call half and half, which is 1/2 the Hartree-Fock exchange plus 1/2 the LSDA exchange or the Slater exchange plus the correlation LSDA. How come the correlation energy only enters here and not over on this side? Any guesses? It seems like I'm being unfair to correlation. I've got exchange in there twice, but correlation is only in there once. Anti-symmetry? Not really. It has to do with the fact that where these two halves are coming from. This is coming from the real limit, so I need an approximation to the real system. What does the real system have? It has anti-symmetry. I'm trying to approximate that with this. And it has correlation. Electron motions aren't really described by a single Slater determinant. The electrons really kind of avoid each other. That's coming from here. This is the other half. This is the limit where lambda equals 0. This is the fake limit where we're basically saying Hartree-Fock is correct. Electrons don't interact, at least beyond the average kind of way that they interact in Hartree-Fock theory. So in Hartree-Fock theory, electrons don't really interact and they're not correlated. And if that is your truth for lambda equals 0, then you don't need a correlation energy because you've declared for lambda equals 0, Hartree-Fock is correct. So we don't need it, so it's not there. So that's why the correlation only comes in once, is because it's only coming from the case where I'm looking at the real Hamiltonian. All right, this is called Becky half and half. This has been done in the literature. It's not the most common way to do it anymore. It turns out you can do better than this. For example, this is just LSDA over on the right. Let's put a generalized gradient approximation in there instead. And I can get something better, and that's the last thing I'll end with. There's a rather famous exchange correlation energy functional called Becky 3. I'll show you why it's 3 in a second. 1 minus a some real number, EX LSDA plus A times EX Hartree-Fock plus B times delta EX E88 plus 1 minus C E sub C LSDA plus C delta E sub C GGA. All right, what is this? This is the Becky 3-parameter exchange correlation functional. 3-parameter because I've got A, B, and C as my 3 parameters that I can vary. What do I plug into this? LSDA exchange, that's that row to the 4/3 thing, that's easy. Hartree-Fock exchange, I can compute that if I have a Slater determinant of cone-sham orbitals. I can get the exchange energy out in the problem using K integrals. This is a Becky 88 exchange energy correction. So the Becky 88 exchange energy would be plugged in here, multiplied by some constant B. LSDA exchange, this is just this VWN functional. That goes here, multiplied by this. And then there's additionally some additional correction factor for a GGA corrected correlation functional. Normally, this guy that's substituted here is the Li-Yang power correlation functional, L by P. So you have Hartree-Fock coming in here. You have local spin density approximation from uniform electron gas here and here for exchange and correlation. You have gradient correction to the exchange energy, and you have a gradient correction to the correlation energy. And all right, so you've added 5 terms. Maybe it's slightly messy, but each one of them is easy to deal with independently. You just add them all up, multiply them by some constants, and you're there. By tuning this in various ways, you could probably have a dozen ways to try to figure out what those parameters are. Becky has his choice of those parameters, and that gives you the Becky 3-parameter function. And I've got a typo here. It's supposed to be 3. Sorry, I wrote 8 or something. I was about to write Becky 88, I guess. B3. So, for example, B3 LYP is that where I substitute Liang and Parr GGA correlation here. This is probably a good place to stop. B3-LIP is the most famous density functional of all. Why? Because it's not insanely complicated, and it gives really good answers for many, many systems. It does fail where cone-sham DFT fails. So I mentioned charge transfer states earlier, or Rydberg excited states. You need to do some extra work to try to patch it up for those kind of things. But if it's a normal molecule and you're doing thermochemistry and trying to compute delta H or get a geometry or vibrational frequency, you do really well with B3-LIP. And so it's very popular for that reason, and rightly so. All right, there's other functionals out there I don't have time to tell you about, but hopefully this gives you a little bit of a sense of kind of what's a little bit of the math behind the scenes and sort of what are the kinds of ingredients that go into these. There are other ones called meta GGAs that throw in the second derivative of the density in hopes that they'll be a little more accurate, and sometimes they seem to be a little more accurate, but it's been a challenge to try to find new tricks that improve a lot over B3-LIP. It's pretty darn accurate. It's hard to beat it. You can on occasion, and you will have trouble if it's a special case where DFT has a lot of trouble, but for general routine kind of stuff, it's pretty good and hard to do a whole lot better without getting really elaborate with your functionals.